Hello and welcome back. Lecture 9-2, Reconstruction. The objectives for today's lecture are to summarize various reconstruction techniques and to demonstrate how to use reconstruction to obtain an original signal from the sample. In the last lecture, we discussed ideal and impulse sampling, and that analog waveforms are too large to be stored in a computer, so you have to quantize or store the discrete signal through sampling in order to transfer the data. But then you will have to reconstruct it once you get on the other end of the system. So in reconstruction, we can see that x of t can be reconstructed from the samples xs of t if ts is small enough or fs is large enough. Basically, it's the Nyquist frequency that we discussed in the last lecture. There are several methods that can be used for reconstruction, including the following. The first technique is multiplexing. So you would have two signals here, and you have a switch that alternates between them. And it would go through these synchronized switches. Which is also called a shared channel or bus because the data is shared between the two different signals. And then there's a switch on the other end, which outputs the two samples. Or you could use digitizing. This looks similar to what we drew for the last lecture, where you have x of t, and the input is through a switch, where the output is xs of t. And that now goes to an analog to digital converter in order to quantize the data to reduce the memory to be able to transmit it. And then that goes through a computer with some kind of digital signal processing to get this binary representation of x of t that you can use in the computer. At every ts seconds. And then on the output, it goes back through the digital to analog converter after it's been processed in the computer, so that you get the output, the sampled signal. And the last method is modulation. So now you have an input m of t that goes through a switch. And you get this frequency representation that has to go through a bandpass filter. And at the output, you would have m of t cosine 2 pi n over tst, which you can then use to reconstruct the original signal. So remember, you have to have a frequency so that you can reconstruct the original signal without losing any of the information. And the way we do this is we have to determine the appropriate frequency. So if omega s is greater than 2b, which is the bandwidth of the signal or the maximum frequency, or fs is greater than the bandwidth divided by pi, the Nyquist frequency, we can reconstruct the original signal x of t after sampling as shown in the following figure. So you use the sampled signal using any of the methods we've summarized earlier, and then you send it through a low-pass filter, which would have a frequency response h of j omega, and the output would be ys of t. So assume we have a strictly band-limited signal, x of j omega, that has the following arbitrary shape with negative b, 0, and b, which represents our maximum frequencies. Then our sampled signal, if you sample at greater than the Nyquist rate, or fs greater than 2b, your sampled signal will look like the following. Where each of these represents omega s, negative omega s, and so on. if you sample at exactly the Nyquist rate, your sampled signal will look like the following. And so on. So once again, this is 0 omega s and negative omega s. So now what you should observe with this second one is that in order for me to retrieve the original signal back, I am going to have an ideal Brickwall filter to reconstruct the original signal. Now we've already discussed that it's not possible to create an ideal Brickwall filter. So you really need to sample at greater than the sampling rate. So going back to this first figure, when I sample at greater than the Nyquist frequency, let me label the bandwidth on here as well. So this would be B minus B. This value here is omega s minus B. And this value here is negative omega s plus B. And you will see why we need these labeled in the next step. So just to summarize, if omega s is equal to 2b or fs is equal to b over pi, you are sampling at exactly the Nyquist rate, and you would need an ideal Brickwall filter to reconstruct the original signal x of t, which we know it's not possible to implement it with real-world components. Or if omega s is less than 2b or fs is less than b over pi, we cannot reconstruct the original signal x of t after sampling as shown in the following figure, because this is called spectral overlap or aliasing. So here's what it would look like if you sample at below the Nyquist rate. This would be xs of j omega. So here's the original signal. And you now would have aliases like the following. Which now, if you think about filtering, you're never going to be able to filter out the original signal because there will be interference from those copies. So, assuming that you have an ideal Brickwall filter and you sampled at exactly the Nyquist rate, then h of j omega, or our low-pass filter, would look like the following. With a cutoff frequency of B, and the output of the system, y of j omega, would be exactly a replica of our input signal as long as the gain on the low-pass filter yields the amplitude of A back. But a more realistic model is for the low-pass filter to look like the following. And now you're going to sample at higher than the Nyquist frequency. So now you'd have minus B here. You'd have B here. It now has a transition band like a realistic low-pass filter. So we would also have here omega s minus B, and here negative omega s plus B. And this would be our pass band edge. And this would be our stop band edge. And now the output y of j omega would also give you back your original signal, negative B to B. And remember, we have selected the gain such that if the sampled signals had an amplitude of A over TS, then the gain here would be TS in order to get A back. So for an ideal low-pass filter, h of j omega is equal to TS rect of omega over 2 pi over TS, or TS rect of omega over 2b, which means h of t, the inverse Fourier transform of h of j omega, is h of t is equal to the sinc of t over TS. Therefore, ys of j omega is equal to xs of j omega times h of j omega, or in the time domain, ys of t equals xs of t convolved with h of t. So the discrete time convolution, ys of t, is equal to the summation from n equals negative infinity to infinity of x of nts, delta of t minus nts, convolved with h of t, which can be rewritten as the summation from n is equal to negative infinity to infinity, x of nts, h of t minus nts. So ys of t is equal to the summation from n equals negative infinity to infinity, x of nts, sinc of t minus nts over ts. So the following sketches show how the impulse sampling and the resulting signal using the interpolation of all the missing values can result back in the original signal. The result is the sum of the delayed sync pulses with a coefficient of x of nts. And this is how we do reconstruction. So let's make a plot of what this looks like. So here's our vertical axis in the time domain. And now we're going to have an envelope. This would be like the envelope of the original signal, which we could label as y of t. So each of our samples is going to be a sync. So our first sync would be here. And it would be sync of t over ts, x of 0. And the zero crossings would be at ts, 2ts, 3ts, 4ts, and so on. And same on this side, negative 2s, negative 2ts, negative 3ts, and negative 4ts. So our next sample with the sync is going to be at ts. So right here, here's our delayed sync, and its zero crossings will also be at multiples of ts. So it would be here. And here. And this is sync of t minus ts over ts, x of ts. And then on the other side, we would also have one here at minus ts, where the zero crossings are at multiples of ts. And this is sync of t plus ts over ts, x of negative ts. And you would continue to do this. And when you add all of these together, it reconstructs to y of t to get the original signal back. So in conclusion, a discrete time signal xs of t always has a periodic spectrum xs of j omega. For the special case where xs of j omega is band limited to b radians per second, the harmonics of x of j omega and xs of j omega will not overlap, provided omega s is greater than 2b, or fs is greater than b over pi, where b over pi is the Nyquist sampling rate. Fs over 2 is the Nyquist bandwidth. The goal is that we want ys of t to be exactly like x of t. Can we make sampling such that we can reconstruct x of t perfectly from xs of t with no information lost in sampling? And we can, as long as we sample at greater than the Nyquist rate, because when you sum all of these signals back together for ys of t, you would get x of t back. And this concludes lecture 9-2 on reconstruction.